Okay, Shailaja, now I hand over the microphone to you. The stage
Thank
is all
you.
yours. Thank you.
Thank you. Let me share my screen. Are you able to see my screen?
Yes.
Okay. Yeah. So sorry for the session right before the bank holiday and the long weekend. I really didn't think through that. I next time I try to avoid in the long weekend so you can enjoy. Uh, So last session we started system design of the message queue. We covered in high level design. Then we were going into the depth for each and every component and how are we going to ensure the scalability, availability, everything for each and every component. And then today we cover the leftover one, that's the storage and some other more good to have concepts that we can explain during the system design interview. Yeah. So last week we discussed the consumer groups, partitions assignment to consumer groups and producers to brokers, everything. We will again revisit in very high level when we are done with each and every topic in detail. We'll come back and explain things in high level overview again for recap, for ensuring that you are getting the flow correctly. Now let's go to the storage. So in the message queue, how the data is going to come, if you think through that. So this is the message queue. The producers are creating the messages, say message 1, 2, 3, so on. Consumers are reading from somewhere. So let's say consumer 1 is reading here, consumer 2 is reading here, so on. So if we see, all the messages are up and only, they are kept on coming up, and there are no in-place updates. So there is no API we are providing to the end users that's going to let them go and update an existing message somewhere in the middle. That means no in-place updates. And coming to the deletions, for the new data, there are only up and only messages. Coming to the deletion, how do we delete messages in the message queue? We have a retention period. Let's say 1 week is the retention period. Then after 1 week, let's say these are the new week messages, these are the old week messages. Then we can have a background process which comes and keeps deleting the older week messages. So that means it's a kind of deleting in the batch from the beginning of the message queue to a batch. So there are no in-place deletion. We are not allowing any kind of API or the functionality which lets keep this message active but deletes this message. This kind of functionality is not needed in our message queue. We don't need it. That means the delete operations are in the batch and in the that's like once in it can be a background process, only one process. It's not like many different incoming APIs are doing that. No, there is no one API deleting here, another API deleting here. That's not what we are supporting. There is only one process, just some couple of internal processes which are coming and batch deleting. So if you see, when you're designing the storage, these three things you need to think through. What is the data insertion criteria? What is the update criteria, and what is the delete criteria? If you think through, that in this high level, this is what helps you to choose the right storage pattern for your design. For Kafka, this is the case. For some other design, it could be different one. And this is one thing. The second thing if you need to think through when you're designing the storage for any system, what the write, is it write heavy or read heavy? In this case, in case of the Kafka, if you see, it is almost the same. Many producers are kept on producing, and many consumers are kept on reading. So messages once produced most likely going to be used once by the consumer, sometimes more than once, because if there are many more consumers, there can be many one message can be read multiple times by different consumers. So it's a kind of a little read heavy, but it's equally write heavy, because messages are very short. This could be just small 1 KB, but there are many more messages kept on producing. So the throughput of the variety is quite high. So in this case, this system is both write heavy and read heavy. And these things, once you list it out for your storage design, you need to observe the pattern. What is a storage pattern here? If you see, all the active messages, the alive messages, are contiguous and in the sequential order. So we need to have a storage which supports sequential writes, keep append only sequential writes, and sequential reads. That which is good for this kind of write and read pattern. That's what we need to choose. Probably you already are already aware of what kind of storage is suitable for in this design, but I want you to think through like a typical interview. So let's evaluate different possibilities here. Let's take first, let's evaluate the first one, the database, the simplest one, because it's a database. You can simply start your MySQL instance on your local host and start trying doing the POC. So usually first people start with database. Let's think through database. Is database suitable for this kind of pattern? Any answers? If it is suitable, if not suitable, why do you think not suitable? If you can just answer in the chat window, that would be that will make you to think through why it is not so. Actually, kind of already written here in the notes, if you see here. So database, what happens for this, you really don't need to understand entire design of internals of the database, but it's good to understand what kind of, when do we usually use the database compared to other systems. So in the database, for example, if you take a Oracle or if you take a MySQL, the most of the reasons when we use this for transactions. Second, when we use it for ACID properties. ACID properties is actually implemented using these transactions, write ahead log, so and so, etc. And database is very good for read heavy operations, because but the write is kind of have penalty. So what happens in the database, when you have a table, database do support in place writes as well. It does support in place writes, and the write can be anywhere on the disk, can be randomly anywhere on the disk. So in the, even if you see, take one table T1, when you write one row R1, this row, if it is written here, depending on the internal design of the database, the second row, which is right in the same table R2, this row can be somewhere else on the disk, because the database need to be optimized for in-place writes, in-place deletes as well, so that the internal design of a typical database is not suitable for sequential writes and sequential reads. It's more tuned towards supporting in-place writes, in-place deletes, and ACID properties, etc. So, and also the write is a bit having a penalty, as we discussed before. Whenever we are updating a row, what we usually do, the write operation internally triggers updation of the secondary index tables, internal secondary index tables. So if this row is having 10 columns, if there are 2 secondary indexes on 2 different columns, then one update operation, a write operation in the row has to go and update the secondary indexes as well. So that means write is having a higher latency, and but read is having very good performance in the databases, because once the write is done, We can use indexes to go faster to the actual row and read them. We can have actual row if we have a row ID or the partitioning key, we can go and read them. So for read operations, the database is good. For write operation, there is a penalty. But in this case, in our message queue, database is not suitable because we want something to exploit the advantage of sequential writes. And database doesn't guarantee sequential writes are performant because there is internal design is tuned for different kind of purpose. So let's rule out the database here. And then let's come to the NoSQL databases. So let's say something like Cassandra, DynamoDB. So we discussed this a little before, but I want, because today we are going to have a little shorter session, I'm going to explain this in detail, and this will be useful for you in upcoming designs as well, because once we evaluate trade-offs of the database and NoSQL, we can use the same concepts in the new designs, different designs as well. So what happens in case of the NoSQL database, the internal design? We do have SS tables, mem tables, which are internal, and then we will flush them into the disk as SS table. So we write the records together contiguously in SS table. This doesn't mean one table T1 data is together in entire database. No. SS table is having a size limit. Let's say you can take it something like it's 1 GB, for example. So with this 1 GB data is contiguous, sequential, but the another 1 GB can be somewhere else. So, and how much sequential disk optimization are we taking advantage for our design? This is not in our hands because the SS table size is decided by the system itself. There is you as a user, we don't have any option to choose that. That is the one thing. Second thing is, the SS tables, usually NoSQL, if you see the trade-offs when we wanted to go for NoSQL, for write-heavy systems, are not for read-heavy. Again, it may be useful for some designs, but may not be useful for all the cases. Because what happens in the NoSQL cases, when there is a write operation, we append a record to the SS table, and we append the same record to the its replicas as well, for example. But in case of the read, that's when the read job has to read from 3 different replicas. For example, if the consistency tuned is 3, then it has to read from multiple replicas. Then this SS table record could be slightly older. This SS table record could be slightly latest. Based on the latest timestamp, the read operation has to resolve which one is the latest and which one it has to choose. There are multiple reasons. One is because there can be multiple replicas. Not all replicas may be having the latest record. The second thing is the way NoSQL, it is supposed a flexible schema. So, for example, for the R1 row, let's say there are 3 columns, C1, C2, C3. When you are updating C2, the SS table record stores only C2 value. It doesn't store C1 and C3 value. So there could be a older record in some other SS table, which one is having C1. So when you want to read entire row R1, it has to go read multiple records from different SS table, collage them together, prepare the actual row for you, and return it. That means there's a lot of logic happening during the read operation. That's the reason usually the NoSQL is not so suitable for the read-heavy operations, but the write-heavy operations are good because we're dumping them into the SS table and vanishing from there. But in our case, our system is read-heavy as well. That's one reason why not suitable for us. And another reason, we are not taking complete advantage of the sequential writes and sequential reads pattern we are having in our design. So we want some flexibility on this case. Now we have evaluated both database and NoSQL. We realized that both of them are not so suitable for us. But if you don't have option, then we can go for NoSQL database. Or if your system is, if you're designing a system from the scratch, we don't have many users, then you can start with the NoSQL database because at least it's good for some number of users. And later you can upgrade to the customized design later on, but you can start initial design with the NoSQL. But because in the system design interview, When you say you are choosing NoSQL, immediately interviewer is going to ask you why are you choosing, what are the trade-offs, etc. So you should be able to explain why are you choosing NoSQL or why are you not choosing NoSQL. But in our this case, we are having a better option. So log, sorry, how do I do? Yeah. So the log structure storage. If you attended previous sessions, if you remember the write-ahead logging, how we are going to do is the same pattern. We don't call this as a write-ahead logging because write-ahead logging is kind of general record. Before actual write operation, we do the some intermediate operation for data data durability and faster response to the user. But in our case, we are going to write actual messages. It's not really write ahead, it's really actual write itself. So what we can do, we can take a simple disk, our own disk. Let's say you can simply say your Linux system, and you take a ext3 file system. You create a file f1.bin, for example, and let's say the topic name is xyz. For the xyz topic, you can create a file called topic xyz. And because we want to support partitions, because that is one reason. We want to have parallelism in the partitions. That is one reason. The other reason is any file system do have a limit on the maximum size of the file. So for example, I'm not sure what is the maximum size in the ext3 file system, but let's assume 1 GB, for example. So after 1 GB of size, the file system doesn't allow you to write more data to the same file. So that's another reason you need to have a segment files. Even for the same partition, you need to have the segment files, because one partition can be growing quite into the terabytes as well. So you can say that partition 1, segment 0 or segment 1, and you write to this one in the sequential one. So the producer keeps appending to this file. The consumer keeps reading from the this file wherever they want to. The file offset is the consumer's offset. If they are reading from the beginning, their offset is 0. If they are reading from somewhere in the middle, their offset is, let's say, 100, so on. So, okay. So we can have our own customized storage where we create our own files on the disk, and we are taking advantage of the sequential writes and sequential reads. So with this approach, how the disk is going to look like, if you see, it's going to be something like, for example, topic ABC, partition 1, segment 1. And after this segment 1 was filled, let's say 1 GB file size is reached, then it creates another partition 1, segment 2, and so on. So the latest file is the active file where the producer is writing. Consumer, if they are catching up with the producer, they're probably reading the same file, or they might be reading something older file, and somewhere in the offset from 0 to, let's say, 1 GB, somewhere in the middle of the file, somewhere they are reading. So this is how we can come up with our own customized storage using the log structure storage. That is a sequential appends and sequential reads, and that's how we are going to have a storage for our message queue. And Kafka also does the very similar, same thing almost. So the main advantage, when you say that we are going to do our own log structure, then the interviewer will ask you why. You should be able to mention that because I'm taking advantage of the sequential writes for the write performance and the sequential reads for the read performance. And the whole, how the deletion is going to happen. Let's say this file is older than 1 week, then we can have a process come and just delete this entire file. So you don't really need to go inside a file and delete records. Instead, this file is older than our retention period, just delete this file. So that's how the deletion is also more effective here. And different offsets can be, different consumers can have different offsets, while one consumer reading from this file, another consumer reading from this file. So different consumer groups can have different offsets as well here. So we are achieving all the requirements of our message queue here. Okay, this is the storage for the data. Now coming to the storage, there are multiple angles to the storage. Not only the data, we need to maintain the metadata as well, the state. What kind of state can be? There can be many. I just listed few here. The mapping from partitions to consumers, that is because as we saw in our design diagram, different partitions are mapped to different consumers. So this mapping need to be stored somewhere, because if this consumer is dying, the coordinator should be able to go and assign this third partition to another consumer. So we need to have this mapping persisted somewhere. Oops. That is one thing. And the mapping of partitioning to brokers, that's the Kafka cluster. For example, our message queue cluster maintains that mapping somewhere. Metadata of the who is the coordinator, are they alive, who are alive. So all this kind of state information. For the state information, we can simply assume we are going to use something like zookeeper for as a coordinator, and we can store the state there. If you really want to go more advanced design, or if you want to give more options for the state, the similar to what Kafka is doing in your latest versions, this state can also be stored in our internal system like a special topic. So that itself is a Kafka topic, but it's a special topic where the deletions are not happening and we are writing the state to that. So that's the state and the metadata like configuration and properties for the topic. So the users can configure what is the retention period for a topic, and what are the number of replicas for a topic, so on. So this configuration metadata, this can also be stored on the zookeeper or as a special topic, or in our message queue cluster internal storage somewhere. So this is the storage. Before going to the next section, I wanted to ask, do you have any questions? Are there any questions on the storage design we are having now, or do you have any other questions in this system design? If there are no questions, then I'm going to the next section. So the next section is the once we covered high availability, scalability, and then the storage. Then we come to the specifics. That's a message structure. When the producer sends a message, the message is going to have some format such a way that our internal design can map it to the consumer's topics, so and so should be able to identify if the data is corrupted, or identify the correspond. I mean, the message should have enough fields to be able to work for our design. So one thing is, as we mentioned, we wanted to have a part. We want to provide a partitioning key value, so that can be used for mapping a message to the corresponding partition. This is for distributing the data to the partitions. So this is the partitioning key can be provided by the end user, the producer, which the Kafka cluster or message cluster can use for partitioning them into different partitions. That's one option. And in case partition key is not provided, they can just directly provide the partitioning ID as well. So here there are multiple trade-offs you may need to answer if the interviewer asks you. If you see in our design here, we are following something the same as what Kafka is doing. We are assuming that this partitioning logic is something is there in the routing layer, which exists in the client, the producer, and our partitioning key can be read by this routing layer, and apply the partitioning strategy, then send the data to corresponding partition directly. For example, if the value is 2 percentile 2, then the top message is coming to this partition. Otherwise, if the value is 1 and 1 percentile 2, if the message is coming to this partition, this logic can be there in the routing layer at the client, something like Kafka is doing. That is one option. The other option is, instead of having this in the producer, we can have our own routing layer, similar to our load balancer in the other systems we discussed. That routing layer sitting in our cluster, That routing layer takes the message from the producer, implements the logic, partitioning logic on that message, and sends the message to the partition. So there are two options. One is having the routing layer here versus having routing layer at the producer. There are pros and cons of each of them. You need to be aware of that if when you need to answer this to the interviewer. If the routing layer is here, the main advantage is the producers doesn't need to aware of how many partitions are there, how to assign a message to a partition. So all that logic is abstracted from the producer. Producer simply says that this is a message, just send the message to so and so topic. But the problem, the disadvantage with that approach is the message has to hop here. From here, it has to hop to the here. In this case, the write throughput will go down because the message is copied twice, one from here to here. When is that from? Another time from to here to here. So write throughput will be impacted in this case. Whereas if you're having routing layer here, you can avoid this extra copy. But the problem is the producers need to update their client. Producer clients need to be updated whenever there is a change in the logic of the routing layer. So as a message queue designer, you are going to implement the routing layer, and this routing layer need to be available in the producer client. And whenever there is a change, all the clients need to be updated. In a bigger organizations, updating all the clients is very painful because clients can be sitting all over the company in many different systems. Updating the clients in all over is really painful, but it comes with the advantage of the avoiding one more message hop. So you need to be aware of these options. You can choose any one of them, and as long as you are able to explain why are you going with one strategy over the other. So if I wanted to explain again, interviewer, they are not asking you to design a perfect system with your choices. Instead, they are just evaluating why are you choosing one over the other. Are you able to explain multiple available options and understand the pros and cons of each of them? So that's what interviewer is looking for. So it's good you mentioned different options you think through and what are the pros and cons of each of them. And then in the message queue, coming back to the message queue, then the actual content, the offset, this offset, yeah, in the message queue, the offset, I'm not sure exactly. Does the producer mention the offset, or is offset directly calculated based on the location of the message on the message queue? This I need to think through a bit. Sorry. And then the actual topic name, to which topic message we are sending to, and timestamp, at what time the message is being produced, size, checksum. So anything whenever you're designing something, and you need to always have a checksum, because when message or any data traveling through multiple layers in a system, the corruption can happen anywhere. It could be this corruption, network corruption, it could be any reason. So having a checksum, how it is going to help you when you are sending a message here. This is your message. When you're sending, the producer says that this is my message, and on this message they calculate the checksum. Let's say checksum is C123. And during the design, when it is traveling through the design, by the time it reaches the consumer, anywhere on the storage or on the network, the corruption could have happened. There could be even one bit flip. We never know. Even one bit, which was one, turn it back to zero or zero to one. In that case, when the consumer receives the message, the actual message is not exactly correct. So what the receiver can do, they can recalculate the checksum. Checksum value will differ. The checksum calculation logic is such a way that even if one bit flip happens, the checksum value differs. So the consumer will realize that the message, the header, which says that checksum is C123, but the actual content, when checksum is calculated, the checksum is 1 to 4, then immediately consumer realizes that this message is corrupted. it can send this bad message to the special topic called dead queue letter, or send a escalation, on call escalation to the organization to look into this case. So instead of processing a bad message, you can always flag them and handle them. That's the reason anything you design always have a checksum plan for that one. And then labels are tagged. So for organizations, different producers probably are having different labels and tags. For example, what is the product line, what is the business organization of this team, this message, so this product, so and so. There can be different labels and tags. So whenever you are designing something, always keep few bytes aside for labels, tags, and etc., to take care of this kind of situations. Anything ad hoc, you can just put them into the labels or tags there. So this is a way typical message structure is. The actual message structure could be having many more fields. You don't need to explain everything to the interviewer. As long as you're able to explain the important fields you think you need to have and why you wanted to have them. But actual real systems could be having many more fields, so you don't need to worry about all of them. Now we discuss this message structure, storage. Now come back to the performance improvements. This is the additional one. These are something like we explain the basic system design. Then if we have time, that's when we are discussing about how we wanted to improve our system if possible. Either interviewer may ask that, okay, when you say that this is my design, okay, let's see where are all possible improvements we can make. Or if you're having time, you can discuss about the improvements, but keep them aside for later. If you keep explaining them upfront, even before going through the end-to-end design, you will be spending a lot of time on this one. Actual design will get impacted. You may not get sufficient time for that. So these are all these sections are good to have. If you have time, or if the interviewer asks you, you can explain to them. So let's come back to this now. After we in high level go through our design. So we are done with the system design. We will look into the performance improvements a bit later. Now let's just look into the overall design, end-to-end ones. So the producer is a client. That's a simple application. Could be simple Java application, Python application. It could be anything. In our example, in our previous session, we assume that, for example, on Amazon, there is order system, there is a subscription system. The order services is having multiple instances running, and the subscription services are having some producers running, or one producer. And this is how a typical Kafka producer code looks like. So if you see, it's a simple Java application. Just you're saying that this is my topic, and this is my key, and this is my message. So this is the actual message, and the key use it for the partitioning, etc. And you're saying that producer.send this record. And if you want to have some additional metadata or capture everything, you can write them, and you can have some properties set up. Depending on the Kafka or RabbitMQ, there can be different properties. And then if there is a failure, you are handling the failure. Otherwise, you're saying that producer, I send the messages, you just flash them out into the queue. So this is a typical producer look like. This executes as a simple application. It could be as part of a typical ordering service or some other service. So producer sends a message to the routing layer. So sorry, here, if you see, the producer sends a message to the routing layer. As we discussed, the routing layer can be here, it can be here. You need to know the trade-offs. And after that, the message ultimately goes to the actual broker. Then the routing layer chooses the broker based on the partition key value, and broker writes to the actual partition, then writes to the replicas as well. So one message is written to the original primary, and then secondary replicas as well. And then routing at the producer versus that's what we discussed. And then reader replica writes the message, and then leader sends a message to replicas, and Yeah, wait for minimum number of replica writes to happen for the durability. In case if the primary is lost or died, we should be able to recover the message from the replicas. So ensure that at least these many replicas as configured having that message before telling the producer that okay, your message is done now. Then respond to the producer as done. Now, when message arrives to the broker, it falls into one of the partition based on the partitioning key, and the consumers can read from the partitions. There can be multiple consumer groups for one topic, and consumer groups are like different services. Let's say order fulfilling service, or it could be accounting service, so on. If it within one consumer group, there can be multiple consumers. One consumer processes data from one partition. There can be extra consumers in case if one of the consumer dies, it can take over the other consumer, which is idle, can take over, or it can be lesser consumers than the partitions. In that case, one consumer has to do more job. It has to process from multiple partitions. And now there is a state storage for the mapping of this partitioning, consumer groups and offsets, etc. Metadata storage for the configuration information, and the coordination service, which is electing what is the primary partition, what is the where are the replicas located, how many replicas located, if anyone died, what is the heartbeat, if when they died, triggering the redistribution logic. All that is taken care by the coordination service. Then the consumer comes here. If you see, this is how a consumer code looks like. It's a simple Kafka consumer. It's simple application code again. It says that I'm the consumer for this topic, and this is just get me messages. And for each and every message it receives, it just processes that. In this case, we're simply printing, but it does actual processing here. It can asynchronously send message to another service saying that, okay, take care of this message now. And it can mention properties like at least once, at most once, exactly once, kind of semantics, what it wants to do. And the consumer group is determined by the consumer name. For example, if there are three consumers in one consumer group, three consumers in the configuration should have the same name. That's when they fall into the same consumer group. Now, this is the consumer path. You see, consumer subscribes to a topic and they specify from which offset they want to read from, and reads messages. We will talk about the batching just in a while. And there are two options here, push versus pull model, where the cluster pushing messages to the consumer. When a message arrives, the Kafka or the message queue broker sending messages to consumer versus consumer pulling messages from the broker. So we discussed this in the last session. There are a couple of advantages of both options. The push model, as and when message arrives, immediately the message is delivered to the consumer. So it's a low latency. There is no waiting there. But the disadvantages is if consumer with many messages, if consumer is lagging behind, if consumer is having too much of work to do, and when it gets a message through the push model, it's unable to process at that time, it's unable to respond at that time. Those kind of scenarios we have to worry about. In case of the pull model, consumer knows when it is free to take more messages, then it will go and ask for more messages from the cluster and takes the messages and process them. The advantages are it has its own control on how they want to consume it, what rate. Can have multiple consumers and sorry. Yeah. The only problem is consumer can keep trying to pull. Okay, when there are, it's not really bigger problem when consumers there are no, let's assume there are no new messages to this partition 3 after consumer process some of them. In that case, consumer may keep trying to go and ask like give me messages, but there are no messages. So it just is kind of ideal loop, but that's not a big disadvantage compared to the other one. So now we had a look at the producer and consumer path, both of them. Let's come back to the performance improvements. Are there any questions so far before we go into the good to have options? Okay, looks like today is a silent day. Then I will go ahead and complete other options as well, and then I will free up you so you can enjoy your weekend. Okay. Now, let's focus on the performance improvements. Coming to the throughput, how do we improve the throughput? In the storage, we did log-based storage, the sequential write and read that we did using our own customized storage. So this is good. We did that. The other option is the batching. In case of batching, what happens? The producer sends a messages in a batch, not like a single message. This is to take advantage of the network bandwidth. So if the producer sending message to the message queue, instead of sending one message which comes as a network pocket here, which involves a network send, it can bash couple of messages into the buffer until the buffer fills up, and then send this entire buffer to the cluster. That means in one send operation we are sending more than one message. And this is the advantage from while sending. And then while storing as well, we can store the batch together. So for example, instead of doing one write operation to the disk, we can take, let's say one data block is 4 KB. We can fill the data block with all those messages and then flash it together. That way it's going to be one disk write operation. And at the consumer as well, instead of giving one message to the consumer, you can give a set of batch of messages to the consumers. So you're trying to take advantage of both storage and network using batching of the messages. While this increases the throughput, the problem is the latency will go up. So you need to wait for this batch to fill up. So producer, for example, this message is produced at 1 millisecond. This is a 2 millisecond, 3 milliseconds. By the time batch is filled up, it probably around 10 milliseconds. So the producer is waiting. That means you're increasing the latency. So when you're doing the batching, you're indirectly increasing the latency. What we in a real system, what we can do, we can keep it as a configuration option, so the user can configure what is the batch size they want to. So if it is a latency intensive system, then they can go for lower batch sizes. If it is a really throughput intensive system, they can increase the batch sizes accordingly. So that can be a trade-off and can be given as a customizable option for the customer. And then, yeah, this is the one customized option. Yeah. There are more features to talk about. These are like quite advanced. If you have really time in interview, really wanted to deep dive, that's when you can focus on how the consumers rebalancing is done as consumers are added and removed, and how the partitions rebalancing is done, how partitions to brokers mapping is done. All these advanced topics can be discussed in deep if either interviewer asks you or if you have time to discuss this. But usually it's really difficult to discuss all this in one system design, because it's really complex system. It can take really a long time to just cover the high level design and a bit of the low level design. And then message delivery semantics that we can have, how are we going to support them, and other options like more optional options like failed messages, how are we going to detect them and move them into dead letters that we just now discussed already. Message filtering is just a good to have option. So do you want me to go through this, or do you want to call this as a done?
Shailaja, I have a question. So when we are in an interview situation, what would be the problem statement that the interviewer would give us for
Ah,
which we need to give the solution?
Okay, so actually we did that initial part in the previous session. I think you missed that one. So this is how the system design interview starts. So usually the interviewer gives you a first, they start with a single line of the statement. Simply, this is simply ask, design a asynchronous communication, a message queue system. They intentionally don't give you a lot of information because they wanted to check, are you coming up with a set of proper questions. I mean, to questions to really understand the question thoroughly before starting. Because in a real organization, let's say your director is coming to you and says that, okay, we need a new system in our mini product, we need a message queue. And director probably is too busy or probably doesn't know about the in and outs because they're not always very technical people, and they may vanish from there. So from there onwards, as a senior engineer, as a staff or principal level engineer, it's your responsibility to start dig from there. So what you do, first you talk to multiple people, understand why do you need this one, and then you ask right question, set of questions. What are the requirements? Which who are the customers? What do they need, etc. So that's what they want to test. They are check, are you asking right set of questions to the interviewer or not? So when they give this kind of statement, oh sorry, when they give this kind of statement, then you come up with this kind of questions and you maintain a list of requirements. So you ask them, okay, I understand a message queue is usually where we send a producer sends a message, consumer receives a message. Do you want to have support multiple consumer groups? Do you want to have which kind of delivery semantics? What kind of data retention do we need to support? What kind of throughput should we support? I mean, for example, what is the sizes of our customers, etc. So all these kind of questions you ask to the interviewer. There can be multiple options. You can mention multiple options you can think through, and then you can negotiate with the interviewer what are all the ones you wanted to support in the design. Now you can say that, for example, we can support at least once, at most one, exactly once, but due to the time limitations, I'm going to stick to at least one semantics in this interview. You can negotiate something like that. And then once you both, you and interviewer, agree on a set of limited set of requirements that you want to fulfill in the current design, that's where you start with the high level design. You start with something like, this is my high level design. Now I'm going to deep dive into in each of them and come up with the low level design, something like this. So that's how the flow comes through.
Good. Thank you, Shailaja. I'll wait for the next question. I have one other question. But
Yeah.
anyone else wants to ask?
Yeah, you go ahead. I think there are not many people today. Everyone is in the long weekend, so there are not many questions as well today.
Okay, so it's about the storage area. I wasn't properly paying attention. I think I would. Um, you mentioned about the sequential ordering of the messages, and for which we need to use disk level storage, right? But then before that, you mentioned about the disadvantages of using relational database because of the SSD storage.
Ah,
I'm not very clear about that. Would you mind just quickly?
Oh,
Yeah.
SSD storage not a problem. SSD
Okay.
storage can be anywhere. It could be for the disk. It could be NoSQL database. This is just a replacement for a typical old style disk. That's all. But the databases. So what usually the databases are optimized for example, if you take like Oracle, Teradata, it could be MySQL. Those are supported by typical relational database tables. Like you have a table T1, you are adding more rows, updating rows. So that means they are supporting in place updates. You're deleting rows. That means in a millions of records, you should be able to delete one row as well. So in place deletes as well. And they need to support transactions like begin, commit this transaction. So those are optimized for ACID transactions. So those databases usual internal design. I wouldn't say all databases are like that, but most of the databases internal design is optimized for a different purpose. So you don't have really control about how those records are stored in a database. For example, in a one table, if you're having 10 records, these 10 records can be scattered very different places on the disk. It could be one record could be one disk, and the record could be another disk. So database doesn't really ensure that all the records of one table are written together in one sequential way. So to take advantage of our system characteristics, if you see, we discussed these are our system characteristics. We are the producer doing only append only. Uh, there are no in place updates, no in place deletes as well, and consumers are reading in a sequential way. So there is a certain characteristics which are very good for the disk. A typical disk, if you see a disk is having a typical disk, sorry, the disk performance, read and write performance is very good when you keep reading it sequentially, because disks are having arms. If you remember our old operating system diagram, this is how disks are. There are plates and there is an arm. This arm is like a old cell tape record, keeps reading like this. So the disk read and write performance is very good when we keep doing in a sequential manner. If you need to jump from one location to another location, the arm has to move. So this arm move takes few, maybe just nanoseconds, but if you keep repeatedly doing this, you're not taking the full potential of a disk operation. So you're writing one row here, another row writing is happening here, then few nanoseconds are taken in between for the arm to move from this to here. So instead of that, if you are doing sequential writes on the disk, the arm keeps moving in a sequential manner. It is done with writing on this plate, then it keeps moving here, then it keeps writing. So that's the reason disks are usually very good for sequential write and read performance. Whereas the databases usually does abstraction. The actual MySQL database can be internally having many different disks internally. It probably having its own partitioning strategy or a mapping strategy. Probably it's writing uh, table T1's record R1 here, R2 here, so and so. If you are using database for Kafka or message queue records, one record can be on this disk, another record can be another disk, or even on the same disk, other record R3 can be somewhere else. It need not be contiguous or sequentially adjacent to the R2. So we are not really taking advantage. It's not that a database doesn't work. It works for very minimal small systems, but we won't be able to achieve the throughput we need for a typical message queue of to support at the customers of the organization level, because we are unable to achieve the high throughput required for our message queue. So that's the reason we go for the disk-based system, which is append only and keep writing in sequential manner and reading in sequential manner.
So does that mean, let's say we use AWS,
Hmm.
would we use AWS S3 for storage? Is that how it manifests?
Okay, so actually that's S3 storage design we are going to have in the upcoming session. Where you will be able to understand that in more detail. But S3 is again something like it's a customized storage. So when you are having S3, and S3 gave you, let's say from S3 you got 10 TB as you bought the 10 TB storage. And when you're trying to write to the S3, it's an object storage. So it will have multiple, for the cloud, it will have multiple data centers, multiple appliances attached, racks. Let's say you're having many appliances, racks attached. When you are trying to write, probably it will try to get a bit of the sequentially a chunk of the disk in one location. It writes, takes that chunk for you and writes, let's say it's 1 TB, it writes 1 TB here. And when this is filled, there is no guarantee that the S3 is going to get you the next adjacent one for you. It may get from another appliance. It can be on the same on this appliance. It could be in a different location, because the S3 is trying to, what it is trying to do is trying to abstract the storage. And second thing, there can be multiple customers using the same storage. So it's a multi-tenancy. So you are a customer C1, another customer, let's say it's me, C2. I bought a 5 TB storage. My data can be sitting right beside yours. We never know because this is totally abstracted by S3 using their storage layer. And your data might be going to some other location. So there is no guarantee S3 is going to really do all your data, going to write all your data sequentially on the same disk. So there is no throughput guarantee. If it happens sometimes, then you are lucky, but the S3 never guarantees you for that.
Okay. So what is the alternative? I mean, in practical sense,
Ah,
when we configure Kafka, where do we specify the storage, and
it could be
what
your
kind
own.
of storage?
It could be your own local file system. It could be your own
Right.
Linux ext3 file system, or your own. In case of Windows, it could be your own, let's say on your Windows laptop, it's C drive, D drive. You can just take one drive and give it to that Kafka, saying that write on this drive, and it will keep your actually for your Kafka. You are just creating a files. So for your message queue, you're creating a file F1, let's say. When you're creating a file F1, the usual typical file systems, they tries to keep the data together as much as possible. Again, depending on the file system logic internally, all the entire file need not be located together. Some chunks of the file can be in one location, some chunks of the file can be in another location on the disk, but the typical file systems tries to keep the most of the data together for a file.
Ah, okay. Yeah. So probably we don't need to actually specify like S3 or anything in the
Yeah,
configuration.
so
Yeah.
for message queue,
Mhm.
simple your
Yeah.
disk is good
Yeah.
enough.
Okay. All right. Thank you, Shailaja. Appreciate that.
Yeah. So let's go to the calculations, because many people we didn't do the calculations last time. Uh, okay, this is my calculations. Oh yeah, it's more from here. So ideally, we usually give estimates before starting the high level design. But last time, because this is our first system design, all of you may not be aware of how to make these calculations well. That's the reason I kept it postponed for a bit later. So assume. Usually, you can ask the interviewer what is that, what are the numbers you wanted to support. So, how many topics? What is the volume of the data that our system can expect, etc. That you can ask, or you can say that if they are saying that, okay, let's assume that it's a Google kind of corporation. In those cases, you can guess numbers. Okay, typically how many messages a Google can have, or you can just assume big enough numbers to ensure that your system is supporting the throughput and the high scalability. So in this case, I assume, let's say we are having 10,000 topics to be supported, at least minimum 10,000 topics, and each of the topics are having at least 1 million messages per day. I'm just assume that I'm something like an Amazon system where I have a 10,000 different products. Each of the product orders are falling into different topics, so 10,000 topics, and for each of the order, let's say 1 million orders coming for each of the product, let's say. So how many total messages are we going to have? Let's just for in this example, let's just take the average message size of 1 KB. You can assume whatever the number you want to. These numbers you can change. Those are never fixed, but just make sure you know how to make this calculation. That's all important. Now, how do you calculate throughput? Throughput is how many messages how many requests, user requests you are getting per second. So, assuming that we are having 10,000 topics, in multiplied by 1 million messages, that's like 10 lakhs a year. 1 million messages totally, how many zeros? So I'll try to make calculations easy for you who are not so great in maths. Don't get confused, just calculate number of zeros. Also, when you are assuming numbers, either take in the powers of 10 or take in the powers of 2. That makes it more easy for your calculations. And is the interviewer do understand that, because that's how we usually make calculations internally as well. We do round off. There is never a perfect number. So if you see, there are 4 zeros here. If you see 6 zeros here, totally 6 plus 10, 10 zeros, 10 power 10. So 10 power 10 messages per day. If you calculate per second, because throughput is usually calculated per second. So how many seconds in a day? 24 into 24 hours into 60 minutes per hour into 60 seconds. This comes around 80,000 or 90,000, but we usually, for simplicity, just assume like a 1 lakh or like 0.5 million. So that's like 10 power 5. Now, when you divide 10 power 10 divided by 10 power 5, we are doing division. So just do the subtraction, 10 minus 5. That means the remaining is 10 power 5. 10 power 5 is 1 lakh, 0.1 million messages per second. This is the throughput. That means this minimum number of messages per second we need to support. Yeah, our system has to support. Then we need to calculate how much data we are going to receive per second. If we see the number of messages, totally 10 power 10 messages per day into 1 KB size, that's like you can simply assume 1 KB is actually 1024, but we round it off to 1000. That's like 10 power 3. Let me use the pencil. Okay. So 1 KB, we do round offs, because we won't be able to do real calculations in the actual interview, which is difficult for both you and interviewer as well. They will also get confused, and we are not very good mathematicians, to be honest. So 10 power 10 into 10 power 3. If you see the KB, you usually convert to the TB or GB. You can simply say MB as well, but for better understanding, you can convert into TB. The power, this KB, if you see 10 power 3 almost into 1 KB becomes 1 MB. Ideally, it's 1024. So you take 3 zeros every time. You bump up the KB to MB to MB to GB, so on. So KB to MB, take off 3 zeros here. So 10 power 10 minus 3, 10 power 7. 10 power 7 MB. Then take off 3 numbers, then you go from MB to GB. So this is the order: KB, MB, GB. These are just a simple tables you will get online. Just remember once, not a really difficult ones. So MB, take off minus 3 zeros, then you get GB. So my 7 minus 3, that's 4. So 10,000 GB. Again, take off 3 zeros, you get TB. 10 TB per day. This is the data we are getting, 10 TB per day. Now, let's assume our data retention period. That means our message queue is going to store the data for 30 days, and after that, we are going to batch delete them, because we just archive them or delete them. Just assuming we are delete them after 30 days, that means 30 into 10 TB per day. That is 300 TB data we totally store at any point of time, because 10 TB per day, and we're having such data 30 days. And after 30 days, our process kicks in and just deletes them. So 300 TB data we need to store. So this is a storage we need to support. Minimum, this is a storage we need to support. And assuming this is just for one copy of the data. But as if you remember our design, whenever we get a message, we are storing that message into the replicas as well, because of the durability. Primary dies, we should be able to record the data from the replicas. So assuming 3 replicas, the 300 TB for one copy, 3 copies together becomes 900 TB. So total storage, including replicas, is 900 TB that we need to support. We should plan for that much storage. That means in your real system, before starting the planning your feature, you go to the infra teams and tell them that this is what we are expecting our feature to be consuming. So give me 900 TB of the data on your Hadoop system or your disk system, whatever it is. You go and ask the infra team. You will place this request upfront, because usually infra teams plan for the organization an year before. So after you implement entire feature, after that improve team is unable to give you the storage, then your feature cannot be rolled out to the retail production. That's the reason we usually make the calculations upfront. Then coming to network bandwidth, if you see 10 power 5 messages per second, that is what we calculated here. Where is it? Here, see, 1 lakh point 1 million, 10 power 5 messages per second into each message size is 1 KB. So totally, again, as I mentioned, when KB to MB bump up, take off 3 zeros here. It's always very simple. 3 is a magic number here. Okay. So take off three numbers, 10 power 5 minus 3, that is 10 power 2, that's 100 MB per second. This is a network bandwidth. And with replicas, 300 MB per second. These are very high level calculations because the real system can have much more network bandwidth and maybe storage as well, because state storage is involved, metadata storage is involved. Not only the replicas, we probably have backups and many more things are going on a real system. But we don't really need to worry all of them. All that interviewer is expecting you to be able to make these calculations upfront and able to think through this. The actual real system numbers are known only after when we really have all the insights of the entire system. So that's really difficult during the system design. So the high level numbers you should be able to explain, and interviewer should be able to understand how are you making these calculations. That's all important. um, does anyone have any questions in the calculations?
Should you not also specify the CPU limit of each VM where the messaging queue runs? Because how do we know that each topic can support 100,000 messages per second?
Okay, so that's exactly, we have the partitions. So one topic, because if you see the one topic is having almost 1 million messages per day. Per second, it's coming to the throughput. This is the CPU bandwidth we will need all together. It means that one machine, all the machines together, we will be should be able to support 0.1 million messages per second. Now, to be able to process 0.1 million messages per second, definitely one CPU is not going to work. That's a because of that, what definitely, that's the reason usually we make these calculations upfront. But if you see and come to the design we made, we have split the topic into multiple partitions, and one partition is each partition is sitting on a different broker. One broker is a one real machine. That means each machine, let's assume each machine is having a at least three cores. The actual corporates have a higher end machines. They might be having more cores, let's say 10 GPUs, 10 CPUs, etc. Then one portion is on one broker, or multiple portion on the multi broker. With this design, what happened? When the CPU of one broker is not sufficient, our design has the flexibility of deploying one more broker and moving those portions to those brokers. So we definitely know that one CPU is not sufficient to process the throughput we are expecting. We need to distribute the one topic to multiple partitions. So we have given a design which which giving the flexibility to move partitions to different brokers as needed. This is what is important.
Yeah, very good. Thanks, Shailaja.
Any more questions on the calculations? We will be doing many more designs, many more calculations like this. So if you are not good in the numbers, don't worry. But in case if you are not able to understand something, just please ask questions.
Do you share the link to this Excalibur anywhere?
Excalibur, I don't have paid subscription, so I just have the local files stored. If you want those files, I can save them. But instead, I was sharing the screenshots because I just don't know if the content I am writing is not something like I'm generating entire content on my own. Some content is something like from the Kafka, etc. And I'm working for a corporate. I just don't want to get into those disclosures or everything. So I'm just sharing the screenshots on our internal Slack channel instead of
Ah,
sharing the files as it is.
okay.
And I'm just a bit over worried. That's all.
No worries. Thank you.
Yeah, if you don't have any questions, then we can wind up. We are almost out of the time. And in case if you anyone want to have more details, if for example in this one which we didn't cover because it's really good to have advanced one, you can ask these questions to ChatGPT. It nicely explains to you. Or still, if you are unable to get, you can reach out to me on one-on-one. I usually have free slots created every Sunday morning around 10 a.m. for alternate weeks. So that's like two slots for one-on-one hard hoc sessions a month. I can share the calendar and you can book a slot if you want anything to be specific or in person. It need not be technical. If you want any guidance on the career interviews or how do you want to plan your career further, etc., you can just reach out to me.
Okay. Thank you, Shailaja. Thank you very much. It's always amazing to see women helping each other out. And even, I haven't been part of all each sessions. I was also able to understand a little bit, even if I'm not a software developer. So thank you very much. And also for the generous offer of helping out even during the weekends. So thanks a lot. It was a great session. Thank you, everybody. If you do have any further questions, just follow whatever Shailaja said. You can reach out later via Slack to her. Thanks so
Yes.
much.
Thank you so much, actually, for giving me an opportunity to share my knowledge to others. So for the sessions, it's a bit difficult for me to tune them because if I tune them for the beginners, people who are experienced gets bored, and if I tune for the advanced people, I don't want beginners to feel like left over, and especially I want to focus on the beginners because I want more and more women to succeed in the career. So that's my primary criteria at this time. But if you are into the advanced engineer or if you are the very beginner and you either of you not able to understand anything, feel free to reach me. I will share my calendar for one-on-one explanations if needed.
Awesome. That's great. Thank you so much, Shailaja. And thank you, everybody. I hope you all have a nice rest of the evening and see you at the next session. Thank you.
See you. Bye.
Bye.
Okay.
See you. Bye.